to say that about if you're going to the dinner this evening, that you don't have to be here at 6:30 to walk to the college. That's an option. If you wish to do that, you can meet at 6:30 here and walk slowly to Emmanuel and have a tour around it. If you don't wish to do that, just turn up at Emmanuel. I'm sure you're capable of finding it. By about 7:15, I would advise, for dinner. Okay. So, does size matter? It's a very important question in many areas of social endeavour. So our next talk is by, I'm going to try his name, Marijn Heule. Is that
pretty close? Yeah.
Any Dutch people out there? I think you would describe Marijn as an extreme combinatorist. So he is somebody who runs towards combinatorial explosions rather than away from them. Would be a way of putting it. And if you think your proofs are big, wait till you see his.
Thank you. Thanks for the introduction. I think whether size matter, at least size sells. I think that's one of the things that I learned. And of course, having the largest proof ever is kind of maybe a dubious kind of record. But still, people came to me and said, "I think I have an even bigger proof." And
so I added an extra line at the end of your
for those people that might think so, but imagine that now I actually solved another problem, sure number 5, which I have a 3 petabyte proof now. So if you want to come to me in which you claim that you have a bigger proof, just make sure you have it larger than 3 petabytes. So some call it large. Tim called it disgusting. I guess that's the reason why he's no longer in the room. I would probably call it rather clever and automated, and so I will tell, because it's actually very difficult to make a proof which is as short as 200 terabytes for this problem. So originally I tried so the original title of the paper was Solving and Verifying the Boolean Pythagorean Triples Using Cube and Conquer, which I think was a very good title because it explains what the problem is, and also that we can solve this problem, and not only solve it, but we can actually make a proof, and that we can also verify the proof. So what the size indicates, and what is very important here, is that we can deal with very big and hard problems. And maybe, so if there's one takeaway message here, because I've seen now the talks over here, people have been using automated tools, and in interactive theorem provers, and mostly how they use the automated tools is that they can use it has to be solved in a second, or in a fraction of a second. And the cool thing about SAT solving, what I can tell you, SAT solving is in the basis of many of these automated tools. SAT solving is not only very good in finding a solution in a second or in a fraction of a second, but it actually, if you give it more time, it actually progresses and progresses and solves very hard problems. So you can just run it on a big cluster and solve bigger and bigger problems. So SAT is not only good for small things, but also for very big ones. So this was a kind of interesting what I got from Larry's talk also, that so these SAT solvers actually was originally made for verification. Actually the first application was, what I know, was actually the Dutch trains, the safety of Dutch trains in the 80s. They made SAT solvers, and of course it is a killer application in formal verification to find bugs in hardware and software designs. It's used in forensic security, hash
killer application isn't quite the right word.
Thanks. Security, bioinformatics, automated theorem prover, we already heard of it. Andrei Voronkov, the author of the strongest theorem prover around, he called actually his solver Vampire a pimped up SAT solver, because SAT solving is actually what's mostly going on in there, by finitizing the first order formulas, also what Jasmine was talking about. It's also, for example, the Cyber Grand Challenge was won by For All Secure, and they did, I think, in order to solve it, they solved, I think, 19 billion SAT calls in order to find exploits. It's very powerful also for hard scheduling and planning problems. And for example, it also really changed the term rewriting termination community. So how does it work? I guess probably everybody in the room knows about propositional logic. I'm not going to ask hands for people that don't know it, but and if there will be very little propositional formulas actually on the slides. But how it works, you have this problem nicely in a higher order logic or somewhere. It's typically kilobytes in size. Then you translate it into propositional logic. It becomes sometimes gigabytes in size, and then you give it to a SAT solver. The SAT solver solves it in some seconds, minutes. Typically, it's faster than most of the people here can write a parser that actually parses the formula. And then once you find a solution, you translate the solution, you decode it back to get a solution for the original problem. So that's the typical thing of how it works. Now, I'm going to explain to you how you can do it for mathematics, and I will illustrate it based on the Pythagorean triples problem, so I will explain what this problem is. Then I will briefly explain to you what is SAT solving, what's the state of the art. Of course, I have very little time to do it, but I will actually focus on how to get linear time speedups for SAT solving, even if you have thousands of cores. And then, of course, we are here for proofs, so I will talk about how to in parallel generate big proofs and also how to verify them. And this problem or the solution got quite some media attention. I will talk a bit more about size, truth, and aliens, and then draw some conclusions. So first, the Pythagorean triples problem. So the original problem, or people started thinking about, dates back from the early 20th century, when Schur started to ask questions about coloring the positive integers. For example, will any coloring of the positive integers with two colors, let's call them red and blue, result into a monochromatic solution of the equation a plus b is c? Now, let's just focus on only of the solutions from 1 to 5, over the numbers 1 to 5 for a, b, and c, and then there are 6 solutions for the equation a plus b is c. Now we start trying to color them, and so number 1 has to have one color. Say we make it blue. If we make it blue, then we see 1 plus 1 is 2, so in order to avoid a monochromatic solution, 2 has to be red. In order to avoid a monochromatic solution of 2 plus 2 is 4, we have to force 4 to blue. Now 1 plus 3 is 4, forcing 3 to red. 1 plus 4 is 5, forcing 5 to red, and what we end up is a monochromatic solution. 2 plus 3 is 5, all in red. Yeah? So the answer of this question is yes. And actually Schur proved in 1916 that no matter how many colors you have, any finite number of colors, the answer is always yes for the equation a plus b is c. Now, let's look at another equation. A cubed plus b cubed is c cubed. Now the answer is no, because we know from Fermat's last theorem that there are no solutions for this equation. So any coloring of the numbers will be valid. Now, from that time up, and also lots of works in the 50s and 60s, people have been looking at equations and asking the same question. And typically, either there are many solutions so it's easily to say the answer is yes, or there are few to no solutions to easily see that the answer is no. Only one simple equation was still open. A squared plus b squared is c squared. And I just put here the solutions for the numbers 1 to 40, and it's extremely easy to color them such that you don't have a monochromatic solution. Actually, what I did is I colored the numbers blue if they have an odd number of factors 5 or 7, and red otherwise. And for example, for these, that's an easy coloring. And you can easily go up to 1,000, 2,000, 3,000. And so the question has become kind of maybe. Maybe we can do it, at least by hand we can do it for many numbers. And that's why Ronald Graham, because he was also looking at this problem, and in the 1980s he started to offer money for people that solved it, actually trying to motivate them to look into this problem. People looked at this problem, and For example, the best lower bound was by Cooper and Overstreet in 2015, so it was first a few thousand, and they showed that you can color the numbers 1 to 7,700 or 664, such that there's no monochromatic solution. And Myers actually conjectured that the answer is no, so that you can do this indefinitely. So what I do is translate everything to satisfiability, so I also translate this problem to satisfiability, which is actually very easy. How do you do it? We use variables xi for each, so we first finitize the problem, we look for whether it holds for the numbers 1 to n. And if it holds for 1 to n, if the answer is yes for 1 to n, then it holds for all the positive integers, because they're included. So what were we going to do? We pick an interval 1 to n, for each number in the interval we have one Boolean variable. If the Boolean variable xi is assigned to true, I is colored red. If it's assigned to false, I is colored blue. And for each solution of the Pythagorean triple equation, we have two clauses, one stating that either A or B or C is red, and the other one saying that either A or B or C is blue. A solution would be coloring which avoids a monochromatic solution. If it's unsatisfiable, then you cannot avoid it, and then the answer is yes. So what we did is we solved the problem by finding the exact n for which it holds. We showed that we can do the numbers 1 to 7,824 with two colors such that no monochromatic solution, and if you go one step further, it's impossible. Actually, you can do this with the right heuristics. You can do it in a minute, and the best solution we have over here for now is 40,000 hours. So, and actually the difference between the two formulas is only 14 clauses. So you add 14 clauses and the runtime goes from a minute to 40,000 hours. And that's actually with very powerful heuristics and other. It was really quite a challenge to actually get it to this small number of 40,000 hours. Because if you run tools out of the box, I will talk about it a bit later, it might actually be approximately 1,000 times more computational time than what we ended up doing. Now, also, it's always nice to have some pretty pictures, so there's a pretty picture as well. This is one of the solutions, and actually, so this is a coloring of the numbers 1 to 7,824 without a monochromatic solution. And I talked about having two colors, red and blue, so why are there white colors? So the white colors mean that for all the numbers that are white, they can be either red or blue. So it's not that you see here a single solution, but actually see 2 to the power the number of white cell solutions. So that's probably also the reason why it is much more easy to find a solution, because there are lots of solutions. And all of them are gone as soon as you add a single number. So just for maybe, so the left corner is number 1, and then it's +1 if you go that direction, and +100 in that direction. And there are all kind of nice patterns that you can see. I cannot really elaborate here, but for example, the more factors a number has, the more likely it has a color, and if it's prime, it's much more likely to be white, because it occurs fewer in Pythagorean triples. Now, what about SAT solving? How did we solve it? And one of the key things is that you do it using linear time speedups. SAT solvers so the short story here is SAT solvers has been worked on since the work by Davis and Putnam in the 60s, and there has been steady progress, say, till 95. And then we were able to solve formulas with thousands of variables and clauses. And in the late 90s, there was really enormous progress, and these days we can now solve problems with millions of variables and millions of clauses. I will tell you a bit more how to do it. If you want to know more, there's the Handbook of Satisfiability, about 1,000 pages on the subject, and recently Donald Knuth also published a book on it. Officially, it's a subsection of the art of computer programming. It's section 7.2.2.2, but it's 316 pages, so there's a lot of stuff in there, and you can imagine how big the art of computer programming must be. I actually asked him, and when are you going to finish it? And he said, when I'm 102, I have a planning, and actually I think he does, so knowing him a bit. Okay, now I want to try give you a little bit how SAT solvers are working. So conflict-driven close learning, CDCL, is the main paradigm that really makes it possible to solve formulas with millions of clauses, and I have been giving many tutorials on this for 2 hours, and now you get half a slide. So just imagine that you get very little of the big picture, or only the big picture. So how does it work? So we have a big formula, and what we're going to do is we just pick a variable, and you can imagine it, which actually is happening. It's almost random, and you assign it to a value, almost random, and we do this and do this and do this. Hardly any reasoning is there until a clause gets falsified. Then the reasoning starts to kick in. This clause is transformed into a so-called conflict clause that is added to the formula. It changes the heuristics a little bit, and practically the solver starts over. And that's what it does until it either finds a solution or finds learns the empty clause, in which case the formula is unsatisfiable. This has been extremely powerful for large, what I call easy problems, because the only way we can solve these problems is because there are, you quickly find the solution, or there are short refutations. There's no way you can solve these problems without being there short refutations. There's also one weakness: it's extremely hard to parallelize. I will come to that back later. On the other side of the spectrum, we have look ahead. Look ahead works as follows. We start with a formula, and we start really reasoning about which variables we should pick, such that we can split the formula into two by assigning that variable to true and to false, and such that both of these sub-problems are easier, and then we do this recursively until we find either a solution at the leaves or find a conflict. And this procedure is very effective on small but hard problems, but the weakness is that it's expensive, because it's very expensive to reason which variable to pick in every step of the recursion. Now, how to parallelize it? This is actually how you should not do it, but this is the most commonly used approach so far, which is as follows, which is called portfolio. How does it work? We have this formula, and we just give it either to several different SAT solvers or the same SAT solver but with slightly different settings. We run them all in parallel, and then we wait to the first one that's actually going to finish, and then we are done. In order to make it a little bit more sophisticated, they share clauses among them. But that's also the biggest problem between them, because typically they end up searching for different kind of refutations. You share clauses with them, but they are not really useful for other solvers, and they actually slow things down. There actually have been a few solvers at the prior SAT competition that were slower on 48 threads than on a single thread, purely because they drag the others down. The one thread drags the others down by sharing a lot of clauses. So doing this efficiently is very difficult, especially if you have many cores. So the method we propose, and we is also Oliver Kullmann, who's over there, has been cube and conquer. And cube and conquer is a hybrid SAT solving method which combines look ahead and CDCL. How does it work? It consists of two phases. The first phase is the cube phase, where we use look ahead to actually do the splitting and make the search tree. But at some point we cut off the leaves, and at some point we think, okay, at this point there exists a short refutation, and now we're going to send it to the CDCL solver to actually find this short refutation. So what you end up with, you have a formula, you split it using a binary search tree in n sub-formulas, and then run CDCL on each of them. And in contrast to portfolio, there is no clause sharing involved here. Because all of them work on different problems, clause sharing is hardly useful and only seems to slow things down. And that actually is also a very nice feature because you don't need any clause sharing. It makes parallelization very easy because you just send off all the different things to different nodes on a cluster. But, and this is a very important thing, there's a kind of what we call the hidden strength of cube and conquer. And now, again, like the prior slide, let n be the number of subformulas that we created. If n is 1, you didn't do any splits, and then you have pure CDCL. If you have an extremely large n, then actually you have the full binary search tree, and you only did look ahead. Now the question is, what happens if you increase n from 1 to very large? This has been done on the Sure triples problem with 5 colors, a subproblem of that, and we are going to look what is going to happen. If you run this problem with a SAT solver on a single CDCL solver, it takes about 1,000 seconds. Now, what happens if you use look ahead to split it into 10? You see suddenly the run times goes up. And it's important to note here that all the numbers here are solving the subproblems sequentially on a single core. So we can always get further speedups by doing things in parallel. But this is all sequentially on a single core. Why is this the case? Some of these subproblems are almost as hard as the original subproblem or the original problem. So say 700 seconds, and therefore if you add them up, it's actually going to increase the cost. And the interesting thing is, after you split it into 100 subproblems, it's back to 1,000 seconds. And if you go even further to 10,000 subproblems, then you see that it's, say, to 200 seconds.
I have one short question. Is the advantage you get by running the 2 to the n subproblems in parallel, is that included?
That's excluded.
Even that?
Yeah.
But then how can it be so fast in the end?
Yeah, so that's actually the hidden strength is that, so I think the short argument here is that CDCL is extremely powerful to find a short refutation. But if there's no short refutation, it starts learning and jumps through the search space. Look ahead is very good in splitting the search problem, but as soon as there is a short refutation, then it starts continuing to split, and then it doesn't find this short refutation, probably. It must be lucky. And so what happens here, that's the hidden strength of cube and conquer, is that you split until a short refutation arises, and then CDCLs can quickly find it. And that's the reason why you can have this, when you have this speed up on a single core. And as soon as you have that, you can really make it extremely fast and solve this problem in a second by running it in parallel. So the typical thing what you see here is that first it goes up, then it goes down, and then actually it goes up again. And the reason why it goes up, the purple here on the slide, is the cost of actually splitting. The splitting costs are expensive, so at some point the costs go up because the cost of splitting starts to kick in. So the reason why we are able to solve this is because actually you get this enormous speed up by actually splitting into many problems. Yeah.
Can you promise a distribution of, say, times per problem? So when you parallelize it, is there one problem which takes a very long time and a lot of problems which do not take subproblems with the conquer problems?
Yeah, so if you limit yourself to, say, a few splits, and that's actually why people initially thought that splitting is not so useful, is because if you, say, have a 32 core machine, you split it into 32 problems, one of them takes 70% of the time, and there's a little speed up, but not too much. If you actually split it into many subproblems, then you actually see that there is no hard problem anymore, because there cannot be a hard problem, and at most it can be 200 seconds, right? So there cannot be a hard problem anymore if you split it far enough. And so my experience is that if it's, say, hard, so actually what we will see is that for the Pythagorean triples, I split it actually into 70 billion subproblems. Because that's what was kind of, with the heuristic, kind of told me that is kind of the point where it's optimal. So some results. We actually can solve this problem with linear time speedups, even with thousands of cores. The first time we solved it, it was 4 CPU years, but less than 2 days on the cluster using 800 cores. If we would have been able to use all 110 cores, we would be able to solve it in, say, half an hour. And this is, I think, a very important point to take, is that the naive approach, the naive brute force approach, would consider all 2 to the power 7,825 possibilities of coloring the positive integers in that range. And the cool thing is that the subsolver heuristics actually were able to bring it down to 2 to the power 40, which is small enough that we can actually explore them all. And maybe you're wondering, okay, if I would have picked a subsolver from the shelf, what would the results be? So the best state-of-the-art subsolver based on the last competition is Tringeling, which is actually also based on cube and conquer but uses more rough heuristics. It's at least 2 orders of magnitude slower on if you use it on a single core based on some smaller examples. The scaling is poorer, it only has kind of 100x speedup when using 1,000 cores. So actually, instead of using 40 hours as in our case on the same settings, it would have used 40,000 hours. Now, parallel proofs and verification. So far, of course, there was only the very positive story that subsolvers are great, and of course they are, but there's also some negative news, is that some of them are buggy because software is buggy. This also holds for SMT solvers. It's probably worse for QSAT or QBF solvers. They don't actually use the word bug in papers. They use the word discrepancy, which means that you disagree with the majority. And so initially, I think there were bugs in implementation, but if you now look more carefully where the bugs come from, it's actually conceptual errors. People really try to come up with new sophisticated things which go beyond resolution, and you quickly make an error here. Maybe also one anecdote regarding competition solvers was that in the hardware model competition of 2010, the Berkeley solver won by claiming that there was a hardware circuit and there was a bug in it, but it couldn't give any input that actually triggered the bug because of all the techniques that are going on. No other solver was able to do it, so the competition organizer said, okay, this is correct. That next year, same solver, some improvements, claimed that the circuit was correct. No other solver was able to claim anything else, so the competition organizer said that it was also a correct answer. So in the SAT competition, this can no longer happen. Proofs of unsatisfiability are mandatory. If you cannot produce a proof that can actually be verified, you didn't solve the problem. At the hardware model competition, you now only have to have an input if you claim buggy. They still don't have the unsatisfiability, but I hope that other competitions will follow. And of course, the mathematicians in the room, they really don't want to say that, oh, you run this tool for a few years, it said yes or no, and then we just are supposed to accept it. They want to have a stronger justification, and I can really see why. So, I talked a bit about proofs. What is a proof of unsatisfiability? First, a clause is satisfiability preserving with respect to a formula if the formula with and without that clause are both satisfiable or both unsatisfiable. And of course, it's very important that this property of satisfiability preserving is checkable in polynomial time. Otherwise, you can just ask whether the empty clause is satisfiability preserving, and you're done. left a formula, write a proof, say both consisting of 4 clauses. And how does proof checking works? It picks the first clause from the proof and asks whether it is satisfiability preserving with respect to that formula, and if that's the case, then it adds it. It continues with the second clause, and the third clause, and last clause, and if the last clause is the empty clause, which is by definition unsatisfiable, then by transitivity the original formula was unsatisfiable. So the Pythagorean triples proof was not 4 clauses but 1 trillion, in total 200 terabytes, but the good news is that actually it can be verified in 16,000 CPU hours, which can be done easily on a day on most clusters. Now, how do we actually, so what is the framework of solving it? Solving, proving and verification. So it consists of 5 phases. The first phase is the encoding phase. So we have this problem in its original domain and we have to bring it to propositional logic, which is done in the encoding phase. This is, so far in our framework, the only part that is not verified. That is also why in the framework we want to have this as simple as possible, and that also will explain you how we did it for the Pythagorean triples. The result of this first step is what we call the original formula. After that, we start to modify the formula in such a way that we can efficiently solve it, and this is called the re-encoding phase. And that will produce the re-encoded formula, but also a proof why all the re-encoding steps were correct. The third and the fourth phase are the cube and conquer phase. We split the formula into many subproblems, which results in cubes, and we have to make sure that the cubes together form a tautology, such that we are sure that we covered the entire search space. Then the conquer phase will solve the formula under all the cubes, which produces cube proofs, and then in the end we just merge the proofs. And actually how this happens is very simple, is we just use the Linux cat tool to just merge them all, and then we obtain a proof, and then we have a tool chain to validate them. And the nice thing actually, what I'll show you later, is that we can actually do it in different theorem provers now. Let me briefly go over the different phases. So the first phase is the encode phase. We get some problem from original domain, we translate it to propositional logic, and the important thing is that it should be simple. For this Pythagorean triples, you can actually use a handful of C lines, and it might not be verified, but you can quickly kind of convince yourself that this is probably correct. And if you run this piece of code with 7,824, you get a formula with 6,492 variables and 18,930 clauses. And asking it for one bigger, you just add 14 clauses to that formula. And this is the interesting thing. Just by adding these 14 clauses gets you from uncountable number of solutions now. I'm really trying to count them, but it's a lot, and to 0. The second phase is the re-encoding phase. And very important here is that the re-encoding is done, the solving is done completely automatically, but also the re-encoding is done automatically. And so there are 2 things that go on here. And the first one is what we call Pythagorean triple elimination. If there is a triple a squared plus b squared is c squared, such that either a, b, or c occurs only in that triple, we take it out. Why is it sound? Because if we have a coloring for the triples without that one, we can just fix the color of the one that was only occurring in that one. You might think, okay, that is a very kind of problem-specific technique, but the nice thing is that there's a technique called block clause elimination, which occurs in the state-of-the-art SAT solvers, which does this completely automatically. So if you give this problem to a SAT solver, it does Pythagorean triple elimination as a first step. So you don't have to put anything about the problem in there, it just simplifies it. And the second thing what is done is symmetry breaking. If we have a coloring with red and blue, swapping the colors red and blue would still give us a coloring. How can we exploit it? By picking one number, and in this case the best thing to do is the number that occurs most frequently, which is 2520, and we color it red. And the nice thing is that also all these re-encoding techniques, which are in SAT solvers, can be nicely expressed in these proofs. So we have this proof format, we easily check this, such that block clausal elimination and symmetry breaking can be expressed and verified. Then we get the cube and conquer phase. So first we get the cubes. We split it into 70 billion subproblems. This we do also in parallel. First I split it into 1 million subproblems on my laptop, and then I do the further partitioning in parallel on the cluster. And actually the splitting, the cube phase is actually 25,000 hours. So that's the biggest part of the solving time. And that gives you this list of cubes for which should be a tautology.
How do you split?
Let's look at heuristics. Yeah, this is actually that's a very complicated heuristic. I think so. It's probably better if there's time to deal with that question at the end of my talk. I will gladly do it. Otherwise, I take it offline because it's actually not a simple answer. But it's a complicated heuristic.
Why is it called cubes?
The cube. So if you have if you have a CNF, then each part is called a clause, and if you have a DNF, each part is called a cube. The fourth phase is solve, and this actually you pick each of the 70 billion cubes and just run it on a SAT solver. And actually, on average, the SAT solver runs only for 12 conflicts. So the SAT solving times for each of those cubes is extremely fast. And in order to do this efficiently, I have 800 SAT solvers running, and there goes kind of a stream of cubes goes through them, and reusing computation. There's all kind of things going on in order to do this efficiently. So, but there's hardly any interesting CDCL thing going on. It's just because it's only 12 conflicts, it's really quick. And since only one of the subproblems was satisfiable, we could easily compute the so-called backbone of the formula. A backbone is the set of literals that is always assigned to true, or always in all solutions. And actually there are 2,304 literals that are forced to a true value. So if you recall the image, so there was red and blue there, 2,304 of them are forced. There's no way that if you change one of them, there's no solution anymore. And what you see is that these two numbers are in are forced to red, and there is this Pythagorean triple which forced them to blue, and these two numbers are forced to blue, and we have this Pythagorean triple forcing it to red. So so actually there are, just having these two clauses would actually already give you unsat, and you don't need the other 12. The last part of the is validation. What I said, we just can concatenate them with cut, the proof, and which is together 200 terabytes, and then check it. In 2015 we had a paper how to do this in parallel, and this is actually now been implemented in 3 major interactive theorem provers, ACL2, Isabelle, and Koch. And the proof has been independently checked in these 3 theorem provers. So it's not only that initially my C program could do it, but now we can do it in theorem provers. and actually it can be done quite efficiently. But yeah, I can give a whole talk about how to do that, but let me continue now with media part of the talk. So getting closer to what you've been saying. So we submitted the paper to SAT, got accepted, we put it on Arxiv, and a few days later we got an email from Nature that they want to have an article about it, and whether we want to do an interview. I did a 70-minute interview 2 days later, and what I really tried to tell her was what I'm trying to tell you. SAT is cool, linear time speedups. We can these big proofs is not only that it's not interesting they're big, it's interesting that we can actually verify them. As you can imagine, nothing was in the article. Yeah, and this is kind of the comments you get. So 200 terabytes, just about 400 PlayStation 4s. But so so one of the things, because the writer of the article was a mathematician, and then you can get kind of these kind of comments, which they consider that what computer scientists are doing is just ticking off possibilities. And of course we're doing much more than that, because the number of possibilities here are 2 to the power 7,825, which is more than the number of particles in the universe. That's not what we've been ticking off, right? We have been sophisticated heuristics to really make it much smaller. And yeah, somehow, yeah, that's also one of the things I get from mathematicians also about this proof. Somehow the mathematicians have the fantasy that for every problem there is a short proof. But we know from complexity theory that's not the case. Although it probably is not, might not be the shortest proof for this problem, but it might be 20 terabytes. You might not be able to make a smaller proof for this problem than 20 terabytes. There might not be a short proof. And it's actually, we consider it likely that especially for this bound result that there is no short proof. And then of course, although I don't think I have to argue that too much here, whether mechanized mathematics is meaningful, but of course the answer is a clear yes. And but the arguments might not be the ones that most people think about here. So why I think it's yes is that the very same techniques are used in formal verification to prove correctness of hardware and software designs. And actually they were only originally designed to do this, and the math is kind of what comes extra. Ramsey theory is, I think, very interesting topic because somehow it seems that there are no short proofs. If you look at the bound results for Ramsey numbers, even for the small ones that have been written in the 50s and 60s, if you look at the papers, they're really nice with all the many pages of graphs, and you have this case, and this case, and this case, and this case, and it seems there is no short argument. And if you go now to something which is bigger, then you get these enormous case splits, and probably there's nothing really smaller. Proofs of unsatisfiability, the criticism is there, 200 terabytes, what can you learn from that? What is there? But actually there's a lot of useful information. First of all, when you check the proof, not only do you, that the checker says verified or not verified, it also gives you back a subset of the original clauses which are necessary, so you get a sub-problem that is also unsatisfiable. It shows you which are the important variables. I think machine learning can really maybe mine these proofs to actually may be able to get something shorter. And probably, last but not least, we simply cannot afford not having mechanized mathematics. There are very important questions that humans will never be able to answer, and we need the answers, even if we don't understand it and even if there are no short proofs. So SAT solving will probably be able to, and it's already able to compute facts which will be never able to understand. And I think it's important to try to understand them, but that doesn't mean we will be able to do that. And for example, is the correctness of a complicated system. If we have two systems, and for one system we can prove correctness, and we have no understanding, and there's this enormous proof, and on the other system we are not able to do it, then we really want to use the system for which we can prove correctness, regardless of understanding why it is correct. And I think that makes our ability to do so very meaningful. So let's give it a bit further, and we started to think about how to reason about this or talk about this, and we came up with this notion of alien truths. What's an alien truth? Is a truth statement, preferably short, for which only very large proofs exist. And already proving somehow that there is no short proof is a very, very relevant question. And these problems, so of course we can make artificial ones, propositional formulas for which there are only of large proofs, but these things actually occur. There seems to be only large proof for many important questions in formal verification. And we actually propose a whole hierarchy of these alien and human truths. On the top of that we have the human truths, and that's kind of all the classical theorems like Shor's theorem. And if we then go make it a little bit more alien, we come to weakly human, and that's, for example, what we consider the four-color theorem. There's this big humanly made k-split. We understand the k-split, it's only that the 600 or plus cases are then checked by the computer. But there's a very big human component here. The next step is what we call weakly alien. What is weakly alien is that we understand the k-split, we can easily generate the k-split, but the k-split is so big that we can never understand them individually. For the four-color theorem, you could even, a mathematician could really look at all the cases and would be able to understand it. It might take some time, but for the weakly, for instance, for that the number of givens for Sudoku is 17, which is billions of cases, it is not possible to check them as a human, that it's not possible. And then we actually come to the whole alien aspect, and that's ticking off possibilities. We have this giant k-split, but then the SAT solver is mysteriously able to avoid this exponential behavior and brings it down to something which is manageable. And for example of that is what we, for example, the 6 van der Waarden number, which has been shown to be 1132. And we can even go one step further, and which we call strongly alien, if there is a high-level statement such that any coloring or any bicoloring of the positive integers will result in a monochromatic triple, as we've done. We've shown that we have the bound result, but this bound result is the only proof now of that this statement holds. There is no mathematical proof that if you consider all the integers that this is the case. And so traditionally, and also during this week, there has been people really talking about the importance of short proofs, but maybe it's not the right question. Maybe the right question is what makes a problem hard. And I think that should be studied much more. Okay, that brings me to the conclusions. Parallel SAT solving has been very successful. It's heavily used in industry for formal verification, but now it's opening up also for solving mathematical problems. We've seen Erdős discrepancy problem, van der Waarden, 6 van der Waarden number, Pythagorean triples. And the cool thing is not only that we can solve them with these completely automated methods, but that we can also produce proof and verify the proofs and check them in highly trusted systems. And so what's next? I think there's lots of cool things that are next, and I really think we should try to solve problems that are not in MP. And that's already done in first order theorems. And for instance, one of the problems I'm looking now into is trying to solve the Collatz conjecture using satisfiability. It's a more it's complicated, but actually I'm still but I'm very optimistic. But I'm hopeful that this actually can be done. And so, and the other thing, of course, is I think we just started to really use cube and conquer. This is just the beginning of cube and conquer. One of I think the main weaknesses at the point is that the heuristics seems to be kind of, you really need to have the right heuristics. An expert like me can easily do it, but I want to have it working out of the box for everybody here. And so that's one of the things of future work, is that trying to make cube and conquer work out of the box on kind of your favorite problem. And that's it. Thanks a lot. Okay. So this how the split is going on. So look ahead heuristics work as follows. So you have your formula and you pick a variable and assign it to a true value, simplify, 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 and you end up with the formula over here. The next step, what you do is you measure the distance between these two formulas. You do this for all variables, for both true and false. Then you have this measurement. Then you combine them. So you say you take the product and pick the highest product of them. But it's really, so one of the simplifications is unit propagation, which is the most trivial one, but there are lots of additional reasoning techniques that are in those look-ahead solvers. And yeah, so this is maybe the shortest answer, but maybe you get some impression how you do it. How are you actually, so there are several ways of measuring the distance. The distance, you can just say the number of variables that are here. That is a very rude thing that you can do. Another thing what you can do is you count the clauses that are here but not here, which are the number of clauses that have been reduced in length but not satisfied. And if you want to go further, is actually you weight all the clauses that have been reduced but not satisfied, and that's actually what we have been doing. So that's a slightly longer. What?
How do you choose the weights?
That's another complicated story, actually. I think it. Yeah, so it's described in the paper. But so what you do is you try to optimize. You try to measure how much the clauses try to force a literal to false, and then you make for each clause the product of those numbers is its weight. But yeah, but there's complicated things going on there, and actually computing the weights is at least half the computation for this thing. So actually, yeah.
One to the back first.
So what we've proven is that there is a counterexample with n equal 7,825. If you consider that the problem might be exhibiting a phase transition around that number, and that it is actually easier to find a counterexample for larger n. If you chose n equal 10,000, would your proof be shorter in computation?
Yeah. So Moshe Vardy asked me the same question and asked me also to experiment with it, what I did. And so if you increase the number, then you see the size of the proof going down. So because the more numbers you have, the more refutations there are. And I think if n is 100,000, then the proof is 2 terabytes. So it really shows that you see the proof size going down and down and down and down.
Well, the computation time.
And the computation time as well. Although, yeah, the computation, although not linearly, because the formulas become much larger and therefore the look-ahead heuristics become more expensive. But the proof checking at least gets almost linear down. Yeah, but I was hopeful if I get to 1 million, I get it much but I think at 1 million, I was not really able to get it much smaller, also because the computations of the look-ahead heuristics are so expensive at that point. But it's definitely the case that it goes down, which is hopeful for the mathematicians in the room, that probably if you consider all the positive integers, that there might actually be a short proof. Probably not when you consider this, the phase transition point, as you call it, but at least there is a suggestion when you see the proof size goes down if n increases, that there might be a short proof if you consider all the integers.
Yeah. So you mentioned in passing that it's an interesting question how we might know that a given statement is alien. Do you suspect that there are alien truths such that the proof that they're alien is itself not alien?
I think the proof that it's alien is probably more likely to be alien than actually the
So my question is actually kind of a follow-up on that, which is this reminds me of some work of Simon Golden with his HR system and conjecture generation as a large computational problem. Have you thought about applying some of these techniques that come up with interesting problems to solve, whether they're alien ones or not?
I'm not.
It's sort of a dual to what you've done. So you've solved an interesting problem, but it was a known one since quite a while. You said, it's a known open problem. So the question is conjecture generation, automated conjecture generation.
I'm not exactly sure. I don't think I understand your question. Probably it's better to take it offline.
Right at the back.
Maybe I missed it, but did you say how you got to that point for that number?
No, I did not. But,
Yes.
but the thing is, so I used.
You didn't try all the numbers one by one, right? You did something up about.
Although actually for other problems I did it because at some point you have very few cubes that are actually satisfiable and you can easily extend. But in this case it was local search techniques were so fast that actually up till the point the largest satisfying assignment, you can find it if the right local search heuristics, you can find it in a minute, so each of them. So you can actually very quickly come up to the point where it's maximum satisfiable, and so that was actually in this case very easy because there are some effective look-ahead techniques.
Dan.
Jeremy, sorry.
No,
Just,
Dan.
how do you decide how much splitting to do before you?
So what, and that's so the very rough thing here to do is what typically happens to be the best case is that if look ahead and cube and conquer, then the cube and the conquer phase seem to be almost the same amount of time, then it seems to be optimal. So I kind of try to find that point you can measure that you sample and then you see when the look ahead or the cube and conquer phase are kind of similar in time, and that seems to be the optimal point. But there are more kind of heuristics in there, but this is kind of for you to, as a rough thing.
So for this question, the direction of the answer was such that you found a counterexample, but like if the bit had been the other way, so if the answer to the mathematical question had been flipped, do these methods apply?
So you need to have some finitization, and that's also coming actually what I'm looking for the Collatz conjecture. I expect it to be true for all possible values, and therefore you have to have other methods to actually show that it works. But there are other methods of finitizing it, but it's not the elegant one that actually you can express with a handful of C-lines. But there are methods of actually doing it. But so in this case, probably what you want to do is to find some construction method that actually colors. So if you have a construction method that goes indefinitely, avoid it, then you find it. So you. But it's of course
Erdos discrepancy was an example of that, right?
No, Erdos discrepancy is the same. It's the same thing as this. Right? You just.
No, but it was wasn't it unsat?
Yeah, but this is also unsat.
Yeah, I mean, this is also unsat.
Yeah. So it's sat, unsat. Yeah.
Right.
And so, but for oh.
But I mean, there was a larger theorem there. There was a more general theorem there.
Yeah.
Did you look at some other work that was done in the field of
constraints programming with regards to parallelizing solvers, such as parallelized work stealing, for example. So this problem of parallelizing Sage was looked at by the constraints programming community, and they've come up with something that supposedly works very well, which is called parallelized work stealing. And did you try to apply? Did you?
No, it probably is. It might have some similar nature as in splitting it into subproblems. I have to look up how that or what are the details over there.
Right.
I have two questions. Do you need to
You
store it?
should only ask once.
Do you need to store the proof to disk, or do you just stream it? And the other one is you wrote the software all yourself, I suppose. Did you use C or C++? Those are the questions.
C, and yes. So now actually, you compress things and then you uncompress it, check it. So you check things in chunks.
Put it on disk.
Yeah. So but you put it actually on disk.
How big is it compressed?
So the compression, so what you can download, I think is about 100 gigabytes. But so you can actually, because the binary search tree, you can actually very compactly represent, because you have to have, for each cube you have only one integer, because you have a binary search tree. So you can have a much more compact thing than all the cases.
This is just a comment. I think it's really indefensible to say that this is mathematically uninteresting because it's only got a big proof that you can only find with a computer. It seems to me that that's like the decidability analog of saying the Paris-Harrington example of a formula, of a natural formula which can't be proved in piano arithmetic is uninteresting.
Yeah.
So I think
But if I may, one argument which Marijn presented here is that, let's say, we developed this cube and conquer method, which is now of some importance, hopefully. So on the mathematical problems, so the mathematical problems here are actually, even if you find a who cares about the 7x25 and whatever, but nevertheless, so it mattered for the world finally indirectly.
That's exactly what I'm saying.
I'm
saying indefensible. Saying it's uninteresting. That's not, the Paris-Harrington thing is fascinating.
Yeah. Who disagrees?
Take one more question. Right, from our
I think to continue that discussion, I mean, we're in the business of saving labor, and I think having a result like this saves the guy who did the dissertation in 2015. Spending a lot of labor on it.
Yes, he was really happy.
Yeah.
I think it makes some interesting labor on doing the complexity theory.
Okay, let's thank Marijn.